Hey, so welcome back, and this is another daily code problem. So today it's called Count Ways to Build Good Strings, and it's a medium level dynamic programming problem. And so I'm going to give you the kind of top-down memoization approach. I won't be doing the bottom-up solution just because I'm short on time today, but this is more enough to pass the question, pass a coding competition or an interview that you're doing. So yeah, so let's get to it. So basically, all that you're given is 4 different integers here called high and low, as well as 0 and 1. And at first I read this wrong. Basically, what you have to do is you want to calculate the number of different good strings. So it's kind of like a maximization problem, where a good string is between the length of the string is between the range of 3 to, or I guess in this case, 3 to 3 characters. And so it has to be within that character length range. And so it has to be, I think this is a better example of at least 2 characters to at most 3 characters. And that's inclusive in this case. I think they show you, yeah, it's inclusive. And so what 0 and 1 represent is when you can either add a 0 character or a 1 character to that string each iteration. But when you do this, in this example, whenever you want to add a 0, you're only going to add 1 0 at a time. But in the case where you add a number 1 to the current string, you're actually going to be adding 2 at a time. Okay, so first I read this wrong. I thought it meant that you could add at most 1 0 and at most 1 1, but it really means that every single time you add a 0, you can only add you're only adding 1 0, and every single time you add a 1, you're only adding this many at a time. Okay, so it's the number of times, or the number of 1s or number of 0s that you're adding each iteration. Okay, so it wasn't very self-explanatory for me, but that's what's happening. So yeah, so to do this, basically, I first thought it felt very natural to do the recursive solution. And that's typically what people suggest you do, is do the recursion, try to implement memoization, and then if you have time, do the bottom-up solution. So what you have to do is basically, what I did was I want to return the result of some depth first search function that starts at 0. And I was just going to pass in the number of characters I've added so far. And so this is really like 0 as in like the length of the string so far. And so let's go ahead and define this. So DFS, and I just passed an n. And once again, n is equal to the length of the string so far. Okay, and so what you do, and we can draw the decision tree, is initially the length of our string is 0. This is our string, there's nothing in it, so it has a 0 length. And we can either add, I think this is a better example, either a 0 to this, so then it becomes like this, or you can add 2 1s like this. These are 2 1s here. And then once again, you can do something similar where at each step, then you can make the same decision. So we can either add another 0 here to get 0 0, or it could be 0 1 1. Okay, and same thing here. We could either do 1 1 0, or we would have 1 1 1 1. Okay, but what you can see here is that every iteration we have 2 different decisions that we can make. Here, 2 different decisions, and also 2 different decisions. So the time complexity for this will be to the exponent n. But this is very bad. This is horribly exponential. And so this is a common pattern where when you have a recursive solution in dynamic programming, you want to get rid of this to the exponent n and convert it into more of an O of n time complexity by also using O of n space complexity. And this is the memoization approach. And the reason why we can do this is you can see here in this like whatever recursive tree that we're building out, this decision tree, although these numbers, these paths are different, like this is 0, 0, and this is 1, 1, 0, what you're appending downstream is being repeated. Like in this decision tree, you can either decide to add, okay, like 0 or 1, 1, and then same thing here, 0 or 1, 1. And what this is doing is this is like at every step, you're producing X number of different good strings. And so by kind of building this recursive tree or decision tree downwards and propagating the solution upwards, we'll be repeating a lot of the same work because at every step, like you'll be recalculating the number of different strings that you can produce at every given length. Okay, so to represent that, I think it's kind of simpler maybe if I show you the code, and maybe it'll help with the intuition. But so what I did is I first just see, okay, kind of what's our base case here? Base case, and that's if our length of our current running string is greater than our high. And so this means that, okay, this is no longer a good string, and so in that case, we want to return 0. Because if we're out of the range of anything that's a good string, we want to stop right there, and we don't want to add anything, so we're just going to leave it 0. Otherwise, we're going to kind of continue processing, and we have two different paths that we can go down. So let's say like path 1, and then we also have the second path. So the first path is if we want to add, you know, this many zeros to our current running number. And that is, okay, let's just call this depth first search function again with the current running number plus the number of zeros. So this is like adding 0 many zeros. Okay? And so this will produce like some number of different good strings at this step. And so we want to store that in some variable, and I just called it response. That's typically what I call it. And initially, this will probably be set to 0. And then same thing here. We want to do the exact same thing, but add 1 many ones, right? Because this is the input variable that we're given is 1. And so then once again, we want to add 1 to it. Now the reason why we're just adding like the numbers and we're just keeping track of the length and not actually like the given string itself is because it doesn't really matter in this case. Like at first I thought it might be somewhat intuitive to be keeping track of the actual string and keep on concatenating it, but you're never really needed to compare or do like a string comparison like in this algorithm. So I ended up deleting it pretty early on. And so once again, from here, we're going to want to return this response, and it will just propagate that answer upwards. Now, the one thing that you might note is we have to be adding to our response here, so plus equals. Now, you might have noticed so far, at no point is this actually going to return something non-zero. So in this case, we're always returning 0 here. And that's because we need to add like 1 at some point, right? We're only ever returning 0 and adding 0 to it. So to add 1, what we want to do is we want to add, 1 as in like we found a good string at that case whenever we're between that low and high range here. And so we can just do that at this point where we say, okay, let's return 1 if n, the length of our string, is greater than or equal to low. Otherwise, let's just start at 0. And so this just means we already know that it's under the high length or under or equal to the high length. And then all we have to check is the lower bound to make sure that it's within that range. And if so, we want to say, okay, this current length is a good string. And so we add to it. So if we run this, this should work. Yep, it accepts both test cases. But if we run this, we'll actually end up getting a TLE, and you can see I actually hit it with the exact same algorithm. I got time limit exceeded, or actually this one here. And this is because, well, all of that repeated work that we're doing, this is currently like the 2 to the exponent n solution, but we want to do the O of n solution. And so to do that, we have to implement memoization, which we can easily do by creating like a DP hash map. You can also use like an array, but I find this just simpler to code and wrap my head around. And so from here, we have a hash map that will look up any pre-computed paths that we've already visited and found out the number of good strings for. And so what we can do here is we just replace this response variable. And this is pretty like templated stuff here that you do a lot, is you just set dp at index n is going to be equal to this. And then from here, same thing, at n, dp at n, and then we just want to return it here. So rather than having this response variable, we're just going to be updating whatever is at this particular index. Okay, and so if we actually already pre-computed this before, we can return it. So if dp at n, or no, if n is in our hash map, that means we've already calculated the result before, and so let's just return it. Right, we can throw that right up here. This base case, and this is memoization. Great. Okay, I think this looks good. So the only other thing that we have to do is this just wants us to take the modulus of it, just because we can be returning some really huge numbers here. And so we can just do that by saying, okay, let's have the mod, which is 10 to the exponent 9 plus 7. And then we just want to take the mod of this number whenever we calculate it, which I guess we can do right here. Sweet. Or that does not look good. There we go. And here as well. Okay, let's try running that. Looks good. And submit it. So that's today's daily LeetCode problem. So yeah, I'm short on time, so I can't show you the bottom-up approach, but this is pretty good, and it gives you like the O of n space and time complexity. So it's a great answer, and I think you just saw it performs quite well. I think it went away. Yeah, like it beats pretty much half the solutions out there. So yeah, I hope it helped, and good luck with the rest of your algorithms. Thanks for watching.